In this video, I will show you 6 ways for evaluating a limit of a multivariable function, and this right here will help you for your Calculus 3 class, multivariable calculus. Starting with the first one, just plug in. As long as you don't have indeterminate forms, as long as you end up with a nice number, congrats, that is the nice answer. Such as this one, x comma y is approaching 1 comma pi. So let's just plug in 1 for x, pi for y, and see what happens. So we get 1 times cosine of pi over 1 for x, square that, and then plus 2. Pi instead of cosine gives us -1 times 1 is -1 over 1 squared is 1 plus 2 is 3, and we end up with -1 over 3, and we are done. And now for the second way, we will just do algebra, just like the good old Calc 1 days. So for example, the limit as x, y approaching 4, 0, square root of x minus square root of y plus 4 over x minus y minus 4. If we just plug in 4 for x, on the top we get square root of 4 and then minus square root of 0 for y, so 0 plus 4 over 4 minus 0 and then minus 4. You will see that the top will give us 0, the bottom also gives us 0, which is an indeterminate form. So we must do more work in order to figure this out. And to do so, just do the algebra just like the good old days. Here we have a square root case. Let's just go ahead and multiply the top and bottom by its conjugate and hope for the best. So we will have square root of x plus square root of y plus 4. And do the same thing on the bottom. Okay, so this right here is the limit as x, y approaching 4, 0. Just multiply on the top and wait for the good thing to happen. When we multiply the top, this is a difference of two squares formula. We just have to square the first term, which is just going to give us, let me just put down square root of x and then we square that. And then we minus the second term square, y plus 4, and then we square that. On the bottom, just leave it. So x minus y minus 4 times square root of x plus square root of y plus 4. Now check this out. This and that cancel, so we just have x. This and that cancel, so we just have y plus 4. But of course, distribute the negative, so we have x minus y minus 4. This is exactly the same as this. So we can actually just cancel. So we have a 1 on the top, and now it's the time to plug in 4, 0 into here again. 1 over square root of 4 for x plus square root of 0 for y, and then plus 4 for the original from here. Finally, this is 2 plus 2, so we end up with 1 over 4 for the answer. That's it. Okay, method number 3, substitution. Just like in many different areas of math, we use substitution. For this one, it also works out. If we have the limit as x, y approaching 0, sine of x squared y over x squared y, if we just plug in 0 and 0 into here and here, we get 0 over 0. So we will have to do more work. But notice the input is the same right here. So it's a good idea to just put this to be another variable and see what happens. I'm going to let t equal to the input. And here, instead of saying the limit as x, y approaching 0, when x and y are equal to 0, t is equal to 0, right? So that means t will be approaching 0. And then we just have to look at sine of t over t. Now we are talking about the single variable case. And this is a famous limit. Whenever we have t approaching 0 of sine t over t, the result is just equal to 1. And technically, you should do a geometric proof for this. I do have a video on that, so you guys can check that out. Try not to say by L'Hopital's rule, right? Mathematician will appreciate that. Or math professors will appreciate that. Yeah, quote it as like famous result or by one of the famous limits. I think people will be happier. Now, number 4, I call this separable, but the actual thing that we're doing is just we are using one of the limit laws. Have a look. I will tell you though, if we put 0, 0 into x and y, we will get 0 over 0. So you know the deal, we will have to do more work. And have a look. This is the same as that. So we can factor that out. So this equals limit as x, y approaching 0, 0. I'm going to factor this out and put it at the end. So I will first write e to the 2x minus 1. And then here we have the ln of 2y plus 1. And then for the denominator, we have x times ln of 3y plus 1. Now notice we have this times that. On the bottom, we have this times that. Look at this part. They're just in terms of x. This part is just in terms of y. So now we can separate it. So we can look at this as, for the first part, just say the limit as x approaching 0, and then focus on e to the 2x minus 1 over x. And then we just have to multiply by the limit as y approaching 0 of this, ln of 2y plus 1 over ln of 3y plus 1. This is why I call this separable. Imagine earlier we have a plus right here. Unfortunately, we cannot break it down like this anymore. And this is actually just one of the limit laws, which says the limit of a product is the same as the product of the limits, provided that they both exist. And they do both exist. Let me show you this one right here real quick. So for the limit as x approaching 0 of e to the 2x minus 1 over x. Some people just use L'Hopital's rule, but I will tell you though, this right here represents f prime of 0. It's a derivative of some function at 0 because it satisfies the definition of derivative, where the function is just e to the 2x. Yeah, this right here tells you the function. X approaching 0, that tells you the input is 0. So now you can just differentiate that f prime of x by using the chain rule. You get 2 in the front and then e to the 2x. Now plugging 0, so f prime of 0 equals 2 times e to the 2 times 0. This is 0, e to the 0 is 1, and this is just equal to 2. So the first one, we get 2. And truth to be told, if you want to secretly do L'Hopital's rule somewhere and then go from here to here, that's fine too, alright? For this one right here, we will legitimately use the L'Hopital's rule. So for the limit as y approaching 0, here we have ln of 2y plus 1 over ln of 3y plus 1. We will get 0 over 0. So L'Hopital's rule, dy, d dy. So this right here is because 0 over 0, we're using L'Hopital's rule. We will just have to look at the limit as y approaching 0. Take the derivative of the top. Ln of something will give us 1 over 2y plus 1. And remember to use the chain rule, multiplied by the derivative inside, which we need a 2. Similarly, for the bottom, we will have 3y plus 1 on the bottom, and then multiply by 3. Now we can just put 0 into all the y's. Not so bad. So if you do that, you get 2 over 2 times 0 plus 1 over 3 over 3 times 0 plus 1. It's just 2 over 1, which is 2. It's just 3 over 1 is just 3. So in fact, this is just 2 over 3. And you can come here now, times 2 over 3. Multiply this out, we get 4 over 3. And then we are done. Now number 5, the polar method, meaning that we are going to take this from the rectangular system to the polar coordinate system. And when can we do this though? The big hint is when we have x, y approaching the origin. And the reason why we should do... Now number 5, the polar method. And now number 5, the polar method, meaning we are going to take this from the rectangular coordinate system to the polar system. And when can we do that? Well, when we have x, y approaching the origin. It's a good idea. Try it. Okay, let's see why. If you want to get to the origin in the rectangular system, in fact, we have infinitely many paths. For example, we can go along the diagonal line like this, or maybe y is equal to 2x, or maybe parabola like this, or maybe just when x is equal to 0, when y is equal to 0, and whatever this curve is. We have infinitely many paths. So this is not easy at all, because we have to make sure to get the limit being the same along all the paths. Well, if you take this to the polar coordinate system, in order to get to the origin, there's only one condition. That is, r is equal to 0. And of course, in the polar world, not only we have to know r, but also theta. In fact, here though, in the origin, theta can be anything. And usually we keep the theta from 0 to 2 pi. Quick note, some people will want the r to be non-negative. So they will say r is going to be approaching 0 plus. That's fine. Yeah. And some people will say it's okay to have negative r. I'm toward it's okay to have negative r. So it's kind of like up to your instructor or up to the textbook, depending on how you are going to follow their definition of the polar coordinates. In fact, this right here is similar to the substitution, but it's a specific substitution. Here we go. We will have to remember that x is equal to r times cosine theta and y is equal to r times sine theta. And lastly, x squared plus y squared equals r squared. Once you know all three, you should be good to go. Why are these the formulas? Well, I have done a video on that, so you guys can go check that out. The link will be in the description for your convenience. Okay, here we go. This is the limit. X, y approaching the origin. We will say r is approaching 0. And once again, it's okay to just consider 0 plus. But keep in mind though, theta is anything, right? Can be anything. Now, on the top, x to the third power, so here we have r to the third power, also cosine to the third power. On the bottom, we just have r squared. Ah, so nice. Because now you can see this and that cancel, and we have one more of them. So we just have to focus on the limit as r approaching 0, r times cosine to the third power theta. Now, can we draw a conclusion right here? Yes. The reason is because if you plug in r is equal to 0 right here, we have 0 times cosine to the third power theta. Well, this right here, let's indicate that. What's the biggest value that this can possibly have? Just 1, right? Because the range of cosine is 1. When you reach that to the third power, you still get 1. And then the smallest value for this is -1. So I can tell you that the absolute value of cosine to the third power theta is less than or equal to 1. So no matter what theta is, we will never have to worry about 0 times infinity. Otherwise, that will be an indeterminate form. Just real quick, if you happen to get the limit as r approaching 0, and then let's say we have r times 1 over cosine to the third power theta, well, unfortunately in this case, we get 0 times, if theta is equal to pi over 2, then cosine to a third power, this right here will give us 0. 1 over 0, that's no good, right? Also, if you just think about it as a limit, then you end up with infinity. That will give us indeterminate form. So if you use polar coordinates and if you end up with this right here, unfortunately, we cannot draw any conclusion. But for this right here, we have 0 times something with absolute value less than or equal to 1. So for sure, we will end up with just 0. So this is how we can use the polar method to calculate this limit. Now the last method for you guys is the squeeze theorem. And in fact, earlier, we were kind of using the squeeze theorem right here. Some people may want you to write this limit to be in between of 0 and 0, then argue that this is also approaching 0. But I think this right here, it's pretty clear. Because I showed you guys that we have something that's multiplied with something that's bounded by 1. 0 times finite has to be 0. Now for this though, all I did was I changed the y to the second power to y to the fourth power. So let's try to do this with the polar method first and see what happens. If we do this though, we get the limit as r approaching 0, x is r cosine theta, but to the third power, so put it here, put it here. This time for the bottom, unfortunately, there's no nice formula for this. We just have to write it out. X squared gives us r squared times cosine squared theta. And then we add y is r sine theta, and then raise that to the fourth power. Okay, in this case, on the bottom, we could factor out r to the second power. That's like the most we can do. Plus, this is r squared, and we have sine to the fourth power theta. And here, we can cancel r squared with this, and we end up with the limit as r approaching 0. I still have r times cosine to the third power theta. Very similar to this right here. But here we have cosine squared theta plus here r squared times sine to the fourth power theta. Now, if you plug in 0 into r and 0 into r squared right here, it looks like we have 0 over that. Isn't the answer just equal to 0? Because 0 divided by, right, we get 0 divided by cosine squared theta. Well, remember, as I told you guys earlier, theta could be anything. What if theta is equal to pi over 2? Well, cosine of pi over 2 is 0, and that will make this bad. In fact, we cannot draw any conclusion right here, unfortunately. The difference between this and that is we have cosine squared theta on the bottom. If we have theta is equal to pi over 2, that might go to infinity. So cannot draw conclusion. So how do we do it though? Of course, the squeeze theorem. First, I would like to just point out for you guys that x squared plus y to the fourth power, this is always positive. On the top, we have x to the third power. I cannot say this is always positive because x could be approaching 0 from the negative direction. So this is what I can do. I'm going to put an absolute value first around just this expression, x to the third power over x squared plus y to the fourth power. Now with this absolute value, I can say this has to be non-negative. Yeah, indicate that. Then we are going to do some algebra work with the absolute value. We know the absolute value of a quotient is the same as the quotient of the absolute values. But the bottom is never negative, so the absolute value on the bottom doesn't matter. We can just say this is equal to the absolute value of x to the third power, and in fact you can also put the third power right here, because the absolute value of the product is the same as the product of the absolute value. And then over x to the second power plus y to the fourth power. Now keep this in mind. When we are trying to do the squeeze theorem, we will try to show some inequality work. We are trying to show that this is in between of 0 and also 0. Because if this is in between of 0 and 0, then we conclude that this limit is also equal to 0. So now, here is the idea. We have x and x. It would be nice if they cancel, right? I don't want to have the y. And it's good right here because we know this is plus y to the fourth power, which is non-negative. So I'm just going to take that away and compare this with just absolute value of x to the third power over x squared. Now let's think about it. If we take away something from the denominator and this is positive, how do they compare? Well, in fact, this right here will be smaller than or equal to this. Let me give you a quick example. Notice the tops are the same, right? Let's say we have 10 and 10. On the bottom here, let's say we have 2 plus 3. On the bottom, let's say we just have 2 right here. You see how I just take away this 3? Which fraction is bigger? This fraction is bigger because this gives us 5, this gives us 2. So the inequality goes like this. There are a lot more different cases. If you are not familiar with the inequality work like this, you will have to for sure watch the other video on how to show a limit doesn't exist. But for now, we have this inequality. Next, x squared is always non-negative. You can attach the absolute value to it as well. And the reason we do this is because now we can cancel. So this right here is equal to just the absolute value of x. And this is great because we know x is approaching 0, so this must be approaching 0 as x goes to 0. And as we can see, we have this that's in between of 0 and 0, so we can compare and conclude that this is equal to 0. And the idea is that when we have absolute value of something, it's in between of 0 and 0, take the limit. Because absolute value is a continuous function, so we can just focus on the limit of the inside must be also equal to 0 as well. And I think if you write this out, it should be pretty clear. And now you might be wondering, why did we have to do all this work to show this right here is equal to 0? Because earlier when we used the polar method, we got to the point that we have the limit as r approaching 0 of r times cosine to the third power theta over cosine squared theta plus r squared sine to the fourth power theta. And I told you guys, if you put 0 in here times this, and this is also 0, but if theta is pi over 2, it would be bad. So I told you guys this was a sad face. But you could argue 0 times anything divided by anything should be just 0, and that's what we got right here as well. Well, not all the time. You really have to worry about what the angle theta is. Here, let me give you guys a quick preview in the following video. If I change this limit a little bit, let's say if we have the limit as xy approaching the origin of x to the third power over x to the fourth power plus y to the second power. Let me tell you, this limit actually does not exist. Even though you still end up with a similar situation in the polar world, but you really cannot say this is equal to 0 because this right here does not exist. And you will see that the squeeze theorem wouldn't even work for this one either. So that will be in the next video. But now, hopefully this video helps. Best of luck in your Calculus 3 class.